Our topic is image compression using Sparsification technique. First, what is mean by image compression? It is all about size reduction. Then why do we require image compression? Image compression is mainly used for reduction in storage space and high throughput data transmission. The next question that arises now is, what are the practical applications of image compression? There are many applications. Few of them I list out. Number one, biometric security. Number two, urban planning. Number three, agriculture. Number four, defense. There are many more such applications one can think of. Now let me explain the need for image compression. Wired or wireless transmission of uncompressed image data would take considerable amount of time. So image data has to be compressed before transmission and decompressed after reception. Most of the image data compression techniques, both lossless and lossy ones, work on redundant symbol removal. In order to remove redundancy, it is essential to reduce the entropy contained in the given data, and this is amount to information loss. Hence, a trade-off is made between compression ratio and information loss. Let me briefly explain image data sparsing. Redundant symbol removal is otherwise known as sparsing. Image data usually consists of significant information and insignificant information. In addition to redundant data removal, sometimes insignificant information can also be ignored. For example, foreground information sometimes can be viewed as significant and the background information as insignificant. In other words, one can retain foreground entropy in an image and reduce background entropy so that the image is further compressed for transmission and decompressed after reception without causing any loss in the significant information. Background removal in an image for entropy reduction. Image shown above has been compressed to 25% of the original data. In this case, one observes that the background information is meaningless and again it is removed. That is sparsified. Whereas the foreground information is kept intact. One should observe that the insignificant information removal is image dependent and hence one should be able to judge an image mostly based on the ordered dichotomy, wanted information, unwanted information. This is a difficult task, especially if one wants to make it an automatic process of judging arbitrary images dichotomically. Spatial sparsing of image data. For example, consider a rectangular lattice shown on the left. One can get subsample rectangular lattice by removing alternative rows and columns. An algorithm to do this job is given in this slide. Data independent image compression using spatial sparsification. The basic idea behind this approach is that the image data samples present in a priori known position in the array are sparsified, compressed for storage transmission, and then uncompressed. Figure given below shows a sample image and its 25% sparsified version. 75% of the percentage of redundant data, 0 is removed from the sparsed image, and the remaining 25% of original data preserved as compressed version. If the size of the original image is W into H, then the size of the compressed image would be W by 2 into H by 2. Now the question arises, how do we reconstruct the original image from the compressed image? We provide here a novel technique called morphological dilation and erosion for image reconstruction. Let us define these two operations, dilation and erosion. Dilation. For any two gray level digital images, capital A and B, the dilation is defined as the Minkowski's addition, which is defined by the formula shown in the slide. Similarly, erosion is defined as for any two gray level digital images A and B, the operation of erosion is defined as the Minkowski's subtraction given by the formula shown in the slide. Morphological filtering is carried out on the given image using dilation and erosion. Reconstruction of original image from the compressed image using morphological filtering. Step 1. Insert zeros in between the two columns and two rows. This is called zero dilution. Step 2. Morphologically dilate the zero diluted image using a 5x5 neighborhood extended structure. Step 3. Morphological erode the dilated image using 3x3 neighborhood structure. Reconstruct image from the spatially spaced version. The spatially spaced image contains information of alternative pixel value in the original image. The reconstructed image is obtained from the spatially spaced image using an interpolation algorithm, which has been discussed in previous slide, which is morphological filter. From the histograms of the reconstructed image and the original image, one may observe that there is no much difference between them. You can see here the top image is reconstructed image, the below is original image, and histogram comparison ratio 1:4. There is no difference in histograms. The size of the reconstructed image is the same as that of original image. Let us take a solid example for a very large image, which is shown in this slide. Now we are going to compress this image. Now original image are subsampled, alternate rows and columns are removed. The redundant element in this image is 0. We remove 0 element and put non-zero element together. It means compression. Look at that. This is a compressed picture, compressed to 25% of original image. From this compressed picture, we introduce 0 in between rows and columns. It is nothing but sparsed picture, the inverse process. Now this sparsed picture, we reconstruct the original image using morphological filtering. The next slide shows that the picture is a dilated image of 0 dilated image. This is morphological erosion of dilated image. We have studied the statistical parameter of original and the reconstructed image. This is shown here. There is no much changes is there. Most of the statistical parameters of both original and reconstructed image remain altered. There is a difference in a count of pixels without blot. There is a little difference in the histograms of the original and the reconstructed images. Visual quality of the images appear to be the same. Median standard deviation of red, green, and blue components in the different images are considerably reduced. Pixels without blots also reduced almost to half in the different image. Image compression to 25% and reconstruction is acceptable. A reconstruction image from the compressed version. Artificial intelligence based compression algorithm, incommutable contribution. It is possible to compress an image to 1.56% and reconstruct it with a good DSLR. Unthinkable. It is not, but logical image processing system LIPS 4.0 does that. First image, original color image of size 1917 into 1074. Second, the original image compressed to 25%, that is of size 479 into 268 and reconstructed to original size of 1917 into 1074. Third image, original image compressed to 6.25% and the size of 120 into 67 and reconstructed to the original size of 1917 and 1074. Fourth image, original image compressed to 1.56%, that is of size 30 into 17 and reconstructed to the original size of 1917 into 1074. Concept of entropy, visual quality, and trade-off threshold. Entropy and visual quality are the two major statistical parameters associated with any digital image. One can segment an image using the notion of threshold. A region in a 3x3 window is viewed as a single valued region when the difference between maximum and minimum values of the neighborhood is lesser than a user defined global threshold T. For any given image, when T equal to 0, if we segment the image by increasing the value of T, then the entropy would reduce, the visual quality would increase. Trade-off threshold, TOT, is the value of T for which entropy values equals visual quality value. Human visual quantization threshold HVQT is the value of T which gives better visual quality value. This algorithm has been developed by Professor Dr. E.G. Rajan sir on the lines of image understanding by human brain and extensively used to segment high definition satellite images also. Note that TOT values of almost remain same for the original and up to twice compressed images. But thrice compressed images exhibit 50% of visual quality value and 38% of threshold value when compared to those of the original image. Conclude remarks. Image compression is achieved to the maximum of 1.56% of original image, which is unheard of till date. Visual quality is in acceptable range in images compressed up to 6.25% of original image. The visual quality is pure in image compressed to 1.56% of original image. An artificial intelligence based algorithm might improve the visual quality of the image reconstruct from 1.56% compressed image. I wholeheartedly thank the World Innovation Tech Expo Investment Summit 2023 organizers for giving me this opportunity to present my research work. My sincere thanks and gratitude to my mentor, Dr. E.G. Rajan sir, for his motivation and support. Thank you for your attention.